Okay, hi guys. Let's start today's class. I think we'd better start from this section, Principles of Statics. If there are any problem that you're hearing me, please tell me where we chat group or at the meeting here. So I think we should start here a little bit. Uh, I think last time we just stop here, this page. Okay, thank you. Uh, we'll talk about principles and conclusions obtained from long-time practice and from many experiments. They are repeatedly proved by practice and now are recognized without proof. That tells what is the principle, what is theorem, right? So maybe we will talk about 1, 2, 3, 5 principles. So it's a basic knowledge for us to finish our false analysis. So it's pretty important. So please, all you guys should listen to me carefully and thinking enough. And if you cannot totally accept what I'm talking about, please take your time, look this picture, look in the textbook again, and try to grasp all the principles. Okay. So first principle, two-force equilibrium. I think we have finished this explanation. It tells a rigid body. This is a very important prerequisite. The body should be a rigid body, not a deformable body. So a rigid body subjected to the action of two forces can be in equilibrium. The necessary and sufficient conditions are 1, 2, 3, 4, right? The two forces have the same magnitude, opposite direction, and collinear. The last one is the two forces act on the same body. In another word, if we have a rigid body and we know it's in the state of balanced, and there are only two forces acting on this body, then we will have this conclusion. Because it is a rigid body first, then secondly, it in a state of equilibrium, then we will know that two forces must have equal magnitude, opposite direction, and collinear, right? If we see in the reverse direction, if we have a body, we have two forces acting on this body, and these two forces have the characteristic that they have equal magnitude. They have opposites in direction. They are collinear. Then the rigid body must in the state of equilibrium. That is the necessary and sufficient conditions. We have explained this in detail last time, right? So let's continue. So we should know, as far as rigid bodies are concerned, these conditions above are necessary and sufficient. But if the body is not rigid body, maybe they are deformable bodies, then the conditions above are only necessary. You should know this is enough. I will not take much time to explain here. There are very important knowledge point we should grasp. That is double force equilibrium rule. So if a body is a rigid body subjected to forces must be in equilibrium. Actually, I think this means this explanation is not a good one. I think we should. I think last time I have do this. So today I do this again, right? So actually, this double force equilibrium body tell us if we have a body, this body is in the state of equilibrium, and we know there are only two forces acting on this body. Then these two forces must in this conditions. That means they have equal magnitude, they have opposite direction, they collinear, right? So we call that double force equilibrium rod. Because this is very important because later when we do some force analysis from a complex force system, if we can note that some of the body in the system is double force equilibrium, that means we will first know its direction. Although we don't know the absolute magnitude of F1 and F2 is, but we know they will have equal magnitude, right? So that is a very important thing we should know. So let's continue. So the second principle is addition and subtraction of a balanced force system. Actually, this corollary is the important one. It tells us the transmissibility of a force. So in order to save time, we will just look at the conclusion. It tells us because this body is a rigid body, and this line is the action line of force F, then we can freely move its point of application from A to B or to any other arbitrary point on this line. It will not change the effect of this force acting on this body. Do you guys get it? Actually, this principle is let us to know this transmissibility of a force is true, all because the body is a rigid body, right? So we can freely change the point of a force along its action line. So in our engineering mechanics 1, this course, we can change the three factors of a force into magnitude, direction, and I think magnitude, direction, and we will change the point of application into line of application, right? So maybe I can write in Chinese here. Three factors can change into magnitude is 大小, right? Direction is 方向, and we can change point of application into line of application. That means 作用线. You know, from this second principle, we know we can freely change its point of action freely along its action line. So it can be changed into a magnitude, direction, and line of action, right? So that's all the second principle about. Therefore, as far as the rigid body is concerned, the force can be characterized by three elements: magnitude, direction, and line of application. See? That's what I write in Chinese, right? So let's move into the third principle. The third principle tells us the law of parallelogram. Parallelogram. It's very difficult for me to read it clearly. So actually, parallelogram means 平行四边形. Actually, this principle tells us how to use this principle to find two forces is reluctant force. You know, please, you guys see this picture at here. So if we have two forces acting on this body more like a yellow egg, right? Very interesting. So this force F1 and F2 have a common point A is their point of application. So if we draw a parallelogram, we can find a force called R or FR. Then this force has this magnitude and this direction will have the same effect of F1 plus F second to the body. Do you guys know what I'm meaning? I'm trying to talk you to tell you guys. Actually, this principle tell us how to find. That means how to simplify a force system, because we can change these two forces into one force, right? So you can imagine if we have another F third, then we should do two steps. One step, we use this so-called principle. We find FR to simplify F1, F second into just one force. Then we use this principle again. Then we can find another maybe R prime for its reluctance from this R and F second. So we can do this again and again. Then if all the forces all have a common point of application, then no matter how many forces are there, we can simplify it into just one force, because they have the same effect onto the same body. That's the principle mean. It's very useful because we should use this principle to do our simplification of a given force system, right? Actually, for this corollary second, it's not very important because it helps if we have only two forces, then we can use these so-called three equivalent forces intersect at a point, right? So actually, we just have, you can see, actually this triangle is a part of this parallelogram, right? Maybe we can choose the above one. We also can choose the bottom one. It's the same, right? And I'm sorry. This corollary second is important. No. Actually, it means this picture. So you guys look at this long sentence. I'll read it. If a free rigid body remains in equilibrium, under the action of three non-parallel coplanar forces, the lines of action of those forces must intersect at one point, right? Moreover, three forces are coplanar, and the special circumstances forces intersect at infinite and become a parallel force system. So maybe we first neglect this. We just focus on this one. So if it is a rigid body, it's in a state of equilibrium, and only three non-parallel coplanar forces acting on this body, then these three forces must intersect at one common point. Otherwise, it cannot be in the state of equilibrium. You guys can think why this is true, because we can arbitrarily select two forces using this principle, find one reluctant force to replace this F1 and F second. Then this body change into the condition that it only have two forces acting on this body. One is F3, another is FR, right? So from the two forces equilibrium principle we have learned, it is a body, it in the state of equilibrium, and there are only two forces acting on this body. So these two forces must fulfill the characteristics. One is have the same magnitude, right? Second, opposite in direction. Third, they should collinear, right? So that's why these three forces must intersect at one common point. Otherwise, it cannot in the state of equilibrium. No? Do you guys understand that? I think it's not very difficult to understand. Do you get it? So let us
Yes,
move into,
slowly.
okay. Let us move into the second page. This is the proof precisely. The proof that why it is true. I think I have mentioned that. So you guys can look at by yourself. You take your time. So we will just move to the force principle. It has a law of action force and reaction force. So I think there's something you should focus. It tells to any action of one material body, you know? Do you see the difference? It means to any action of one material body, not a rigid body. That means this principle is applied to bodies, not special to rigid body. That's the difference from the up three principles, right? It tells to any action of one material body on another, there is always an equal and oppositely directed reaction. They are equal in magnitude. They're opposites in direction, collinear, and exist together, but that is very important. That's the big difference from the two force balance bar, right? So it act on different body. That's the biggest difference from the two force balance bar, right? So we can see this example where we can find maybe this is very thin slide here. So right here we have maybe a light, right? So if we know it's in the state of equilibrium, then we can do the force analysis. First, when we select this lamp to be object to analysis its force, then we can see the force the string act on the droplet, and this is the gravitational force, right? So because this is the body, it only have two forces acting on this body, and in the state of equilibrium, then we will know that P and F will have same magnitude, right? You have same magnitude and opposite direction and collinear, right? But you can see there is a P and another prime. Because actually this gravitational force is acting object is the Earth. The Earth. The Earth have an attraction force to this lamp. So actually, this lamp also have a attraction force to this Earth. So this P and P prime is a pair of action and reaction forces. You know, so actually, this if we imagine that we cut this rope of this string into two parts, right? Actually, this F affecting objects is from the upper one. Actually, this upper one pulls this lamp, prevent it draw onto the ground, right? So actually, this lamp also will have a pull force to this upper rope. So here you will have another pair of action and reaction force. So we will see that action and reaction force, we can very easily define. There are a lot of pair of action and reaction forces, but we always should know that this F and F prime, this pair of action and reaction force always acting on different body, right? Always acting on different bodies. That's the most different to the two force balanced bar, right? Or two force balanced rod. Because if we see that this is the two force bar, only have two force acting on this body, and it's in the state of equilibrium. We say it must have F1 and F2. It will have same magnitude, opposite direction, and collinear. But you guys will find that F1, F2 all acting on the same body. But here our P and P prime, F and F prime, not acting on the same body. That's a bigger difference, you know? So I hope you guys can understand that. This is very important, right? So that's the principle of action and reaction force. So you can imagine if I push you, so actually your body will have a reaction force. You know, that two force will be a pair of action force and reaction force. We always have action force and reaction force, right? Now this is a fourth principle. Let's see the final principle of solidification. Maybe this one a little bit difficult to understand. So you guys try your best. Let's see what it's all about. It tells if a deformable body is subjected to the action of a force system. So you should focus on this important prerequisite or preconditions. So it firstly tells us if, sorry. So if a deformable body subjected to the action of a force system and it in equilibrium, the state of equilibrium will not be changed, will not be disturbed if the body solidifies. So how you get understand this solidifies becomes rigid. So I think maybe I'll put it in this way. Maybe you guys can understand. So if we have a substring, we know it's a typical typical deformable body because it's common used in our daily life, right? So if we have a jaw force here and jaw force here, and this F1, F2 have the same magnitude of this direction and collinear. We just use our hand to acting these two forces on the substring. So you will find because our manpower is limited. So to some extent, maybe we will find that the substring will elongation a little bit. So when it elongation enough, maybe here, maybe L plus delta L. Because the limited manpower of us, we cannot let it be elongated a little bit anymore. It will keep in this whole length. See, we can see that this state is in state of equilibrium, and this body is a substring. Then we'll keep this F1 and F2 do not change. We imaginary change the substring into a solid body. That means solidified rigid rod. Then the state equilibrium we just mentioned will not change. Do you guys understand? So that means if this substring under these two forces F1 and F2, maybe you guess one of you guys acting on this substring, it's in the state of equilibrium. So we can imaginarily think about that. We can change this sub one into a rigid body. Then this equilibrium state will not change. That's so-called solidified rigid. Not for real, just for simplification, right? But you guys should remember that opposite direction is not true. So I will illustrate in this way. You guys listen to me carefully. We have a rigid body, and we also have a F1, F second, and let this body in the state of equilibrium. Then F1, it's F and F second will in direction, same magnitude and collinear, right? Then we think or we imaginary that we change this rigid body into a soft one. Can this soft one also keep the state of equilibrium? No, it's not true. So you can imagine. So when there is a chopstick, and maybe you guys do not know what is chopstick. It's a tool that we Chinese eating food. Do you know? Actually, two sticks. It's very useful for us when we eating something, we'll use chopsticks, you know? So we can think one of chopstick is the rod, is rigid rod. So we can use our two hand to joist unless this one of chopstick in the state of equilibrium. But if you imaginary think that we change this chopstick into a soft one, a rubber, how to express this? 橡皮泥, you know, a rubber one, then you will see it a state of equilibrium cannot be kept, right? So we should know that. That's the fifth principle. Talk about the solidification. Maybe later we will use this principle to do our force system simplification. So I try my best. I hope you guys can understand a little bit, right? So this principle tells us that the equilibrium of a balanced deformable body can be described by the theory for rigid body. That means if it is a deformable body, it's in a state of equilibrium, we can look at this one as a rigid body, right? But the reverse direction is not true. It's not true. Okay. I think that's all the principle about. We have finished our explanation. It will be our founded base, our basic knowledge points. So I think another important part is we will talk the third section, talk about constraints and their reaction forces. Please, you guys, this section is very, very important because if you learn this section very good, then you guys will find actually the force analysis is very easy because we only need to find how many types of constraints in the force system. And then we draw its reaction forces. That's all. That's all. That's all for the force analysis. So let's look at the concepts. So before I introduce you guys some type of constraints and their reaction forces, there are basic concepts we should know. So first one, we will talk about the free body. What is free body? So there are two things you guys should know. Let's see, I put in this way. So I will draw a three-axis coordinate system. It's very common used here. So we have x-axis, we have y-axis, and z-axis. You know, we can imagine that we have an arbitrary shape body A here. So if A is a body, it's on this space, and no any other give it some constraint. So it can free move, right? We call that actually body A is a free body. So this is very easy to understand, but you guys should know in space 在空间当中 this free body A or another body, it will have fixed types of independent movement. No, it will actually, in other courses, maybe we will call this independent movement with freedom. Freedom. It also means a capable of movement, a capable of movement. So that is, it will have three translational movement along x-axis, along y-axis, and along z-axis. So you guys can think about that. It also have three independent rotation movement. Maybe it can rotate x-axis, have a rotation movement. It can rotate like this. You can see my point here. It also can rotate around y-axis. Also can rotate around the z-axis. So there are 6 independent capable of movement of a free body. So you guys will find it a little bit complex, right? In Chinese, we call that 复杂, complicated. It's very difficult to understand, right? But I have a good news for you guys. Actually, the many of force system, we will focus on a coplanar force system that actually in space is a generalized problem, but we always focus, or we always put our most problems into a plane, coplanar force system. Then we'll only think about one of its plane. Actually, we will have a lot of important focus on this plane. That means coplanar force system. Then when this coordinate system simplified into just have 2 axes, x and y. So we always have this default coordinate system. So x always point to right, and y always point to up, right? Actually, this thing we do not draw here actually is the point the screen onto your face, onto your nose, because we can use right hand rules, right? I think I have mentioned what is right hand rule, right? I have Kater have some question. Last time the example cannot understand. Okay, maybe next class we'll talk it a little bit again, right? I will continue to this new class, right? So, so if we have another body, but this time this body A, it must always in this plane, right? So you guys can imagine if I have a brush, can you guys see my hand? I have a brush. So if I put it onto a blackboard and let it only move on the plane, then it will only have 3 independent capable of movement. We can see it have 3个自由度 freedom. No, the one is translational movement along x-axis. Another is translational movement along y-axis. And the third one will be the rotation around the z-axis, maybe here, So actually, because it always should keep on this plane, maybe just the screen is a plane, right? So it cannot move along the axis. It cannot rotate around X and Y axis, right? So there are three another movement independent movement that cannot be fulfilled in the plane. So that's when we talk about the free body, you guys should know a free body in space have 6 freedom. A free body in the plane only have 3 freedom. So when we talk about the constraint, we will use some type of constraint. Further constraint is some kind of freedom, right? Maybe I can just tell you guys, we have a fixed support. If this is the body A, if this kind of constraint here, then all the 3 capable of movement of A will vanish. You know, because this is a fixed support. It's a kind of constraint we will learn later. Then this rod A cannot move along X, cannot move along Y direction, also cannot rotate around the Z axis. So its freedom from 3 change into 0. That kind of constraint, that is a kind of constraint. That's what constraint all about. No? So actually, there are no absolute free body. Can you have a absolute free body? No, absolutely not. We cannot find absolutely free body. So actually, if a body A in the space, it must have gravitational force from the Earth, right? And other forces. So I think they are totally not have an absolute free body. But you should know when we use this idea free body to know it's independent, capable of movement, 6 in space and 3 in plane, right? When you guys understand what is free body, then we can talk about constrained body. So it contrasts compared from a constrained body with free body. A body whose displacement in space or in plane is restricted by other bodies, either connected to or unconnected with it. So when we talk about the gravitational force is from Earth, maybe the body not in contact with Earth, but when it in state of equilibrium, it must on the ground. Why when we jumped, we have to fall onto the ground again, right? We have to keep in touch with the Earth, with the ground, because the gravitational force, right? So it's called a constrained body. A constrained body is not important. The type of constraint is important, right? So what is constraint? In China, we call that constraint means 约束. What is constraint? What is 约束? It means prevents something happen. Prevents something happen. Maybe my English expression have some grammatical errors, but I really hope you guys can understand what I really want to tell you guys, right? So anything that restricts the displacement of a given body in space, 6 are type of displacement, right? Here constraint is noun, not a word. It calls us constraint is a noun, not a word. Reaction force of a constraint. The force that which a constraint acts on the body thereby. Actually, when we talk about this, thereby restricting its displacement. It called the force of action and reaction forces. So when we do some force analysis, so maybe we have body A and we have body B, this body A, this body B, and this is a type of constraint. Then body A will, from this constraint, have some force acting on body B. Then from the principle of action and reaction forces, then body B must have another force to body A. That means we have a pair of action and reaction forces. Do you guys know? Then after we finish this bit, we will I will introduce some common yield type of constraint to you guys and tell you how to draw its reaction force. No? So let's move on. So the first, the characteristic of reaction force of constraint, maybe it helps you guys have a totally understanding of this. So the characteristics, right? The characteristics of reaction force of constraint, their magnitude is usually unknown. This is true. Actually, we call this constraint's reaction force, it is the inactive forces. They are maybe because there are a lot of reaction forces. They are inactive forces. Actually, when we do the analysis job onto a simple or complex force system, we should figure out the active force first, and then we'll analyze the inactive force. So maybe I can give you guys an example. Can you guys understand from this example? So in Chinese, I don't know what about your country. We have some maybe horse or donkey to do job for farmers. So let me just tell you donkey. So donkey have to eat grass. We have a tool, maybe it's more like a big tail. We drop it into ground, then it have a very long rope. Then the donkey, I'm not a good drawer. The donkey will have 4 legs, right? And a tail. The donkey will eat grass. If we look at this from up bottom direction, we will find actually the donkey will have a round path trajectory. It only can eat grass on this whole circle. Can you guys understand? So if it only movement at this whole circle, interior of this whole circle, it will find there no constant force acting on this force. But if this donkey try to escape from this cave, maybe they are very terrific grass. It have a triangle shape. They want to eat there, right? They try to escape from this circle, then it will be pulled back. That is why we call that reaction force is inactive. If you do not escape from this whole circle, there will be zero constraint force, right? That's why it usually unknown is usually inactive. Can you guys get this? It is an example from our daily life. I think maybe in your country, you maybe have a horse or cattle to do some job for the farmers, right? But these cattle should eat grass, right? Maybe you have a lot of free time. You just draw the rope, let this donkey or horse eat grass freely. But if the man have no time, then we will have this tool. To pin it here, it only have a circle. Maybe we should keep this row long enough to let this circle big enough. Then this donkey maybe can eat a lot of grass, right? So that's why. The second, their direction is always opposite to the direction in which the given constraint prevents the displacement of body. So still from this example, so let's say if the donkey from escapes the circle along this direction, then the donkey here, maybe it will have a constraint force here, F. This force will prevent this donkey escape from this circle, right? Next time, this donkey will try again, but this time maybe it will along this direction to try to escape this circle. Then it will have another constraint force to prevent this one escape the circle. So we will find the reaction force. First, the magnitude is usually unknown. The second, their direction is always opposite to the direction in which the given constraint prevents the displacement of the body. So actually, you can see this reaction force can along any direction around this circle, because this direction totally according to the active force, right? We just use this constraint to prevent some kind of movement to be restricted. So if you know this, then when I introduce some type of different constraint to you guys, you will find actually different constraint will have different reaction force, right? It try to restrict some kind of displacements to not happen. The third point of the application is the contact point between what? I don't know. Between the body and the constraint. Actually, in our course this semester, when we talk about the constraint, we mainly focus on the constraint that one body contact another body. We do not talk about the magic force, you know, because this one and this one it apart have a displace, but it have attraction force from one to each other because of magic force. You know, we do not talk about this kind of forces. We always talk about the two bodies contact here has some have some common point. Then we talk about the constraint reaction force and its direction, right? So actually, I think this page is very useful for you guys to understand the characteristics of reaction force of constraint, right? Then we'll move to this page. We'll talk about some common types of constraint and their reaction force direction. I think today maybe I might be a little bit speedy, right? And it's just 2 minutes to terminate the first class today. So I think it's better to have a rest. So you guys have rest. We will restart at 11:10. Okay?
Okay.
So all you guys have a rest. Okay, guys, our time is up. Let's continue. So first, I think I will mention this example because some of you tell me you still cannot understand this example. It's true that this problem is not, it's very complicated, especially for you guys. Actually, don't worry about that because later chapter we will learn this again. So I will try to uh, explain this a little bit, right? Actually, uh, actually here is a problem. Tells we have we have a first P. At the point of acting is point C. The prerequisite condition is actually this L-shaped body actually on the plane of X or Y, right? But the force is acting on the space. So it tells us to determine the moment for force P about the three axes. Mainly it helps to calculate a force is moment to some axis, right? So we have two methods. The first method is we can use the definition of a force is moment to a given axis. Do you guys still remember? Actually, first we should find the plane. So let me tell this again. If we try to find this force P, its moment to axis Z, right? So first, we will find the plane which is perpendicular to this axis Z, right? Actually, you can find plane X or Y if the plane fulfill our requirements. Second, we should projection force P onto this plane. Then we have a projection force Pxy, right here, Pxy. Then, if we want to calculate the moment of force P to axis Z, it's the same thing. We can just calculate the force Pxy is moment to point O, right? This point O is the plane which perpendicular to the axis Z, right? That's how we change the calculation of the moment of force to axis into a force to some point, right? Then we can use it's maybe you can elongation this pxy. You can draw a line from O to perpendicular to this action line pxy. Then we use pxy times h. We have the moment of this pxy to the point O, right? That's the definition of a force is moment to an axis, right? So actually, this precise is very complicated. We are common useful method is first we decompose this force P into three components, right? That's what I write here. So P actually equal Pxi, Pyj, and Pzk. You guys also can see that in this picture. Actually, if we try to calculate the moment of force P to the axis ZXY, we only need to calculate the three component forces Px, Py, and Pz. Its moment sum to the given axis. You know, that's the first method. It's also a little bit difficult, but it a little bit simplified the precising of the projection force. Because if we know Px, Py, and Pz, so when we calculate the moment to z-axis, we can find actually Pz is parallel to z-axis. Then its moment to this axis will be 0. So we only need to calculate Py to is moment to z, and px is moment to z. Then we only need to calculate the py to point O and px to point O. The same reason is if we try to calculate the moment of P to axis X, because Px will always parallel to axis X. So we only need to calculate Pz and Py. So this whole process is a little bit complicated. For you guys, maybe also cannot totally understand. So I will highly recommend that you guys just have an impression of the second method. I think I have tell you. So first, you should know when you have P, you have this angle information. You should have the ability to find Px, Py, and Pz. This is the basic requirement of all you guys, right? Then we will do not use this method. Instead, we use the important relationship between the force is moment to axis and the same force to the point, right? Actually, we have this method, actually the indirect method, because we can calculate the force P at moment to point O firstly. Then we can very happily find that its three moment actually is the moment of force P to the three axes. So all you need to do this mathematical calculation, so first you get link point O and C to get its position vector R, right? Then please find the three components of vector R. We have -5 along x-axis and 6 along y-axis and 0 along z-axis because the whole vector R is on the plane x or y, right? So we just need to calculate the point P is moment to point O. Actually, it equals vector position vector R cross product position force vector P, right? So you just need to write like this. After you write here, then you should use your mathematical knowledge to have the final result. Also, you can use software calculators. All you want can be fulfilled, right? So because the reason of time, I just tell you guys the first one. The second and third, you will use your time to think about by yourself. So if we try to find this, we can just imaginary clear this row and clear this column. So we have this sub-determined problem. So we have this 6O, Py, and Pz. So because this is 2 plus 2 determined problem, it's very easy, just cross product and -1. It equals 6 times Pz minus 0 times Py, right? It's only equal 6 times Pz. So if we find what the value of Pz is, you will find actually this result will be this one, right? If we try to calculate the second one, you should first imaginary clear this row, second imaginary clear this column. Then we have this determination calculate problem. We have Px and what this we have -5 0 Px and Pz, right? Px and Pz. So this time, because it's middle term, you should remember you give a minus sign first, then do the cross product minus. So it equals this -5 Pz minus 0 times px, so it's 0. Then it also fail pz. So you see, this is 6 pz. This one will fail pz. The third one, you just need to clear this row and clear this column. So we have another sub determination calculate problem. This is px and py. So this time only use cross product and minus this one to this one. So we have minus 5 times py minus 6px. So that's how we finish this problem. If you guys still have problem, you guys still cannot totally understand, it's okay. Don't worry.
Yes, sir.
Maybe
Yes, sir.
later in some later chapter we will focus this problem again, right? So I only need you guys have impression here, right? So I think that's all for this example.
Yes, sir.
Okay.
Please,
So
can you explain px?
okay. Thank you.
Around px equal to I can understand px equal to minus p cos 45 and sin 16.
Uh,
Can you explain this?
I'm sorry, I cannot totally understand your English because my English is limited. So when you just talk to me directly, maybe I cannot understand totally.
Can you
So
yes,
I,
sir.
I
Can you explain this one? I indicate this.
do you mean you don't know why there have
Yeah,
many
yeah,
sign here, right?
yeah, yeah. P cos 45 degree and sin 60 degree. How is
Okay.
this one?
Let me try to explain here. So
Okay.
you can see this picture, right? So do you know if here this angle is 45 degree, you know this pxy should equal p times cosine 45. Do you know?
Yeah, yeah.
You can understand, right? Let me try to write here. So first, you should make sure you guys know actually this pxy, when we do this projection, it should equal p cos times cosine 45, right? So
Yeah.
then we have this. If you cannot understand here, I can draw you guys this again, because I can draw it on the very easy to understand way. So actually this is px and this is py. So that means from the firstly projection, actually we have this pxy here. You know, we have this px here. So this is plane, a picture in the plane. So you will find it very easy to understand. So from this picture, you can find actually py should equal pxy times cosine 60, right? Right? Pxy. So because pxy equal p, you do not reply, you cannot understand. So pxy times cosine 60. Can you understand that from this? Because here is a rectangle, you know? So pxy times cosine 60 degree just means we do another projection along this direction. It's more like that we project this pxy onto this axis. So it will shrink into py. No? Can you understand that? If I rotate this here, maybe it's more like this. We have a pxy. And here is triangle, and this direction is py. And this angle is 60. You know, if we have this triangle, then here is pxy. Then this py should equal pxy times cosine 60. Can you understand? No?
No, I think
You
yes, yes.
can. Right.
That is
Then,
py. Yeah.
right?
The vertical is a py and parallel is a px. Yeah.
Right. Another is px, right? Actually, this px equals this one. So we can just write here px equal pxy times sine 60. Right? Times sine 60. Actually, this is 30 degree. You also can write pxy times cosine 30, also is pxy. So when we do the second calculation, we always should look at its direction. So you can find actually when we do the another projection pxy onto this axis to get px, you will find actually this direction is opposite to the positive direction of x, right? So we have give a minus sign here. And from the same method, we project pxy onto here, you'll find py, its direction is along the positive direction of y. So it have a plus positive sign, so we do not need give this because it's the same thing, right? So that's why here have minus sign. I hope you can totally get it, right? Yes, it is difficult, a little bit difficult to understand, right? So
Yeah,
maybe,
logic.
okay, thank you.
Understand it.
You can take your time, can think this
Please,
through,
please 1 second.
right? Okay, so can we just move into the new things of today's class? Okay. So this time I will tell you guys some common types of constraints and their reaction force direction. I think it's easy because if you know whatever the type of this constraint is, its main aim is to prevent some capable of movement happen, right? Just more like this. So if we have a ball here, we have slope fixed on the ceiling, then this ball cannot drop onto the ground, right? Because the gravitational force, it is active force. This acting object is from the Earth because the Earth have attraction force to this body, this ball, right? So it try to move along this direction, but because of this rope, it cannot happen. This kind of direction movement is restricted. You know, so we call that constraint given by a string or a rope or not a chain or strap or not the soft things. You know, strings can only be stretched. Therefore, the reaction force applies at the point of contact and the direction is all away from the body. That's the very important thing. So you guys can imagine this scenery. So if I told you, please, can you help me if we have a ground, we have a box here, and then we have a rope here. I said, please, can you pull this box A from left to right? You say, okay, that's easy, you know? You will see it's easy. We just stretch this rope and let this rope to pull this body maybe from this position to another position along the right direction. But if I said, Please, you guys, you push this body A, use this rope from right to left. Can you do that? No, right? We cannot do that. We are not Superman. We don't have that kind of power. That means this constraint given by string, a chain, a strap, in Chinese we always call that die, 绳子, right? Sorry, 绳子, 链条, all these kind of things, it's deformable. It only can pull, never push. Can you guys understand? It only can have this direction of, so you can think that T means tension. In Chinese, we call that 拉力. The force to pull, 拉力. It never push, right? Because if you try to push this one, use the deformable things, then this rope will be deformed like this. It cannot acting a force on this body. This body cannot be moved. So it only can be tension, can have tension force. So we call that this constraint given by a string or chain. It only have this. So actually, this is common use in engineering scenario. We have a smaller trolley wheel here, another. When we let this strap fasten enough, then when this one rotation around one fixed axis, this one also have the same direction of rotation movement because of the friction between this strap and this wheel. But if we imaginary cut this strap into two parts, then if we just select the left part to be analysis, then the right part will have action force on this part. We can use some kind of force to denote this kind of action, actually this and this. And from the action and reaction force point of view, then the left part also have action force onto the right part. This is SE prime as second prime. Actually, this is a pair of action and reaction force. And this is also another pair of action and reaction forces, right? So I think the first type of constraint is very easy to understand. Please, you guys remember that it always pull, it's never push, right? So first, we should let this rope should be absolute straight line. Then it can acting some pull force onto the body, right? But when you push that, it cannot be a straight line. Again, it will be more like this. So it cannot transmit force from here to here, right? So this is the first type of constraint. This is a typical example. Actually, what I mean. Actually, could you guess? Can you guess this is the motor, right? 电动机, right? Motor, 马达, 电动机. When we give electric power, this one will rotate maybe like this rotation direction. Then because this strap is fastened onto this smaller and bigger wheel, then because this strap and this wheel is friction force, when this smaller one had rotation moment, and this one will also have rotation moment, right? It's very typical use in our engineering life, right? So actually, when we imaginary cut it into two parts, then it will have F, right? Will have FT. So I hope you guys can understand this kind of 约束 means constraint. This is instance or example. This actually is strap. No? Strap. STRAP. Okay. The second one is smooth contact plane. It's very complicated in English to express something. So that means smooth means we do not consider its friction force here, right? So the reaction force is applied at a point contact and directs normal to both surfaces. So the first one, you can think about that we have a ball just stationary on the ground. You see, the active force P is acted by Earth to this ball, right? It's maybe attraction force, right? Then because of this force P, this ball try to push into the ground. Actually, that never happened because it have a push force because of the gravitational force. Then this ground will have a reaction force. Actually, it is the constraint force of this kind of constraint because that smooth contact plane. Oh, we call that in Chinese. Smooth means 光滑, polished, have no friction. 光滑 contact in Chinese is 接触. 接触 plane means 平面. So this one is the straight line. You can think about it is it is also a circle, but its radius is infinite, right? So you can say actually this, when its radius is big enough, it can be a straight line. Just like our Earth is bigger enough. So when we move around the Earth, we always think that the Earth is flat, not a ball, but actually it's a very, very big ball, right? So I hope you guys should pay attention to 2 points. One is we try to give this reaction force. So first you find the point of contact, then you should draw its common tangent line. You see? So let's say here, this is the body one, have a curved shape here. This is the body second, maybe body second, body one. So these two get contact here. This is the contact point. So we should draw the common tangent line, right? We should draw the common tangent line first. Second, we should draw a perpendicular line and through this point, contact point. Actually, this is a common normal line of these two curved shape. You know, in China we call that normal means 法线, 法 线. So actually, first we draw common tangent line, then second we draw a perpendicular line, which perpendicular to this common tangent line and through the contact point, right? So we can use here to repeat this precise. So this, first we draw the common tangent line here, and then we through the point A, we draw its common normal line, which is perpendicular to this common tangent line. Because this one is very easy, when you are familiar with this process enough, we can just draw this NA here. It's very easy, right? You can imaginary do these two steps in your brain. Do not real draw line on here because we know the final one is this. And this, we also should along these two steps. So first, we should draw this common tangent line here, right? Then we should draw through the contact point and draw the common normal line here. Then our reaction force should always along this direction and try to prevent it capable of movement. Can you guys understand me? Right? So we should know how to draw this kind of reaction force. We should know its direction should along this direction and try to prevent this capable of movement, because maybe this rod want to movement along this direction, and it movement along this direction, movement along this direction. So this reaction force is try to prevent these things happen. Just the like the example I have to tell you guys, a donkey only can eat grass on a given circle, just like this, right? If you always keep in the circle, there no any reaction force. If you try to eclipse that, it will be have some kind of reaction force, just like this. If you try to move along this because of the gravitational force, okay, here, I will give you a reaction force to prevent that things happen, right? That's why it have this kind of reaction force. That's why it's along this direction. You know, that's very important. I hope you guys can totally understand that, right? This is second. So there are typical examples of the smooth contact plane. So here, here, and here. Actually, the third picture is common mechanical uh, mechanical mechanism. In Chinese, we call that 齿轮, means a wheel. A wheel means always do a rotation movement. I'm not sure if this maybe it's not right. So it have teeth here. It will run rotate around some fixed point. Then this teeth will push this teeth in this direction. Then the second gear will rotate around another fixed point like this. So if this is another rotation direction, this one, maybe here we have O1, it have rotation at here. So you will find actually this omega 1 is opposite to omega second. This kind of gear, it have a very important factor. We have the ratio between 1 to second. So we have this is second, this is module 1. At speed of rotation have a ratio here, and 1 second, or its angular velocity omega 1 omega second will be the number of tools they have, z second over z 1. Because when the gear is really manufactured, it will always have the fixed number of tools, right? Teeth, right? So this ratio from the second over the 1 will always be a constant. So that's the big typical characteristic of this kind of mechanical. So this is a very important transmission things in our machines. You know, we call that. But here we just talk about the so-called smooth contact plane constraint. Actually, this active tooth will give a force to this slave tooth along this direction, right? Actually, this slave tooth also have reaction force to this one. from the action and reaction point of view. So if you guys didn't know all the things I have mentioned here, it's okay. I just hope you guys have some impression, because in the next semester you have another course, means mechanical principles. Maybe you will learn this more, right? So anyway, this is the second constraint types. Let's see the third. The third one is very easy to understand. We call that smooth cylindrical pin. In Chinese, we always call that 活动铰链。活动means can move. 活动铰链 means hinge. No hinge. It's more like when you open and close the door, their axes have two things, like here, and here is your door, right? So you can open it, you can close it, but here and here actually is the constraint of this one, smooth cylindrical pin, So this picture is very typical. It's very helpful for us to understand this kind of pin, So this is body 1, and this is body 2. So you can find it have 2 ears, and it have internal hole, right? And this body second also has a hole here. So when we push this body 2 into here, we let this 1, 2, 3 holes has a common internal line. Then we push this pin into this. I can draw it here. So it's more like this. This is body second, and this is body 1. Body 1 will do not movement. It's fixed here. So do you guys still remember we have talked about if a body is on a plane, it only has 3 capable of movement. Translational movement along X, maybe Y, and rotation around the Z axis, right? So you can see, because our default direction of X axis always along this direction, and our Y direction always along this direction, So you can see this body second just more like a donkey. It cannot move along X direction because it pinned here by this pin, right? It also cannot move along Y-axis, but it can freely rotate around this point. Can you guys understand? Actually, this cylindrical pin has 2 kind of reaction force. One is try to prevent movement along X direction to happen. Another is to try to prevent movement along Y-axis to happen, right? So this kind of reaction force, we always like to draw like this. If we just select second body second as the object to analysis, so it will have 2 reaction axes. One is Fx, another is Fy. Actually, these 2 forces is acted. It is acted by this body 1, right? So this time, if we try to analysis body 1, right? Body 1, it will have Fx prime and Fy prime. In my case, we do not think about this pin. So you can think we just fixed pin with this. It also can be free. It's also the same result. So this method of analysis is very simple. So from the action and the reaction point of view, you can find the reaction force Fx and Fx prime is a pair of action and reaction force, right? So this force is acting by 1 to second, and this force Fx prime is acting by 2 to 1, right? That is the real meaning of a pair of action and reaction forces. And for the single body, because it have a cylindrical pin here, it will be acting with two reaction forces, because Fx try to prevent a movement along x-axis to happen, and Fy try to prevent movement along y-axis happens. So I think this kind of explanation for you guys will very easy to understand, right? So this is the cylindrical pin. So you guys should know how to figure out which constraint is this kind of pin and know how to draw its reaction force. No? So this is the pin. So we have a rod here named 1. We have a wheel here named 2. So it will have a common hole with same side. Then we can push a pin into this common hole of body 1 and body 2. Then body 2 will have a relative rotation around this axis to body 1. So if we simply draw like this, so this also is here. So when we select maybe this body 2, this body 1, we just select body 2 as object to analysis is reaction force. It will be XA, YA. So if we also try to analysis body 1 here, so you guys always highly recommended you should draw XA prime here. And YA prime here. Why should we draw like this? Because the later our test is try to figure out or calculate its real value of XA and YA. Because when you draw a force analysis like this, you know XA prime and XA is a pair of action and reaction forces, right? So you will know, actually, if you know its value may be like 10 kilonewtons, then you will immediately know XA prime also will equal 10 kilonewtons. You know why? Because a pair of action and reaction forces will always have same magnitude, opposite direction, and collinear, coexist, acting on different bodies. You know, that's a useful trick, I think. Trick, maybe in Chinese we call that 技巧. So this process will simplify our calculation, right? And this is also the thing. So if we select this rod 1 to be select this would be the objective to analysis. So this reaction forces acting by wheel to rod will be XA and YA. Then this time, the other time, if you try to select body 2, the wheel to be analysis, then because it have a common constraint here, also point A, then you should draw like this YA prime, which have opposite direction from here, and XA prime, which have opposite direction from here, right? The reason is the same from this, because if you have no its magnitude, you will immediately have this YA prime is magnitude. This one also is true, right? This is cylindrical true. Its English name is very difficult for me to understand. It's very complicated, very complex. Actually in China we always call that 铰链或者活动铰链、固定铰链, right? Very often we call that 铰链, maybe some kind of joint, right? It's joint. And we still have 5 minutes. Maybe we can finish all the type of constraint. So this one here, a very useful or typical example for you guys to understand. So 2 years, another body always have a common hole. Push the pin into here, then we have this like this. These two guys can rotate relatively one to another, right? And actually here it tries to tell us a fixed hinge support. It tells this, if this is part of ground, no, it's part of ground. We have 1, 2, 3, 1, 2, 3, maybe 6 bolts. You know what is the bolts? Bolts. Which one? It will fix this body, maybe body second, body 1, will fix it onto the ground. It cannot move. It has 0 freedom. Then the body 1 and the body 2 will have this kind of, just like I have drawn from the previous page. So this is body 1. We call that is fixed hinge support. If we have 2 bodies, they have common constraint here. We have body 1, we have body 2. They all can move. Maybe this point A. This is the first one. Maybe this is fixed. This one is not fixed, right? So please, you know the difference. See? Actually, this is fixed here. Maybe we just we just think this one ground is the total one because always stationary, always don't move. We like call this frame. Frame is the thing that not move from different time, right? So this is a fixed hinge support. Actually, if we select this wooden body as objects to be analysis, so it will have reaction force from ground to this body where this pin. So we have XA and YA to prevent there no a movement along X direction. There are no movement along Y direction. So this body 1 only can rotate around the point A, right? So because it only has 3 freedom, 2 of them are prevented. So only have 1 rotation movement is allowed, right? Do you guys understand? So this is a different view of point. This is also fixed pin. You see, all the 3 things mean the same thing. So this one, always means body 1 can move, body 2 is a frame, right? Body 1, body 2, body 1, body 2. So, you know, we have a triangle shape, but actually it's more like there are 3 pins. So this will always cannot move. It is a stationary frame. So it's more like this. So when we select body 1 to be analysis, its reaction force from the fixed one to it is XA, YA. You know, so if you guys look at this picture, you will find it's very interesting. They're more like that. We have a 2 wheel here. So that means at point B, it allowed to move along X direction. So you can think about that. When the whole frame is temperature is from low, maybe 20 centigrade to 30 or more high 60 centigrade, it will elongation. So if here point A and point B all fixed, then it will have to have some very bad deformation. So if this is fixed, but it can move a little bit, so it try to, because the increase of temperature, it can move a little bit. So try to make the steady state of this whole frame, right? Actually, this is another type of, we call that connected unhinged support. That means 光滑支撑，滑动支撑 ，no 滑动支撑。That means only have one direction of reaction force. You see? All this 1, 2, 3, 4 have the same function, only prevent the capable of movement along axis. But because we have a lot of wheel, we have mechanical here, so it's a little bit movement along x-axis is allowed. So only have one reaction force. You know, I think that's all for today. I hope you guys can have a look to our textbook, because maybe the whole thing we mentioned today is a little bit difficult to understand. We still don't have homework today. Next time we will have to do some homework, right? So I think that's all for today. Bye-bye, guys. Bye-bye. Class dismissed. Okay.
OK 了。
再见。